So now moving on, we take the next binary modulation scheme, which is the binary frequency shift keying. So the two signals involved here are root of 2 EB by TB cos 2 pi FCT, and as you know well, in frequency shift keying, which is basically a frequency modulation scheme, the two signals are differentiated through their frequency. So there will be a frequency difference between the two signals, and that's what differentiates them. And that difference in frequency is depicted like this: cos 2 pi fc plus delta ft. So delta f is the deviation in the frequency, and of course the signals are in an interval TB. TB is the bit duration, or the bit interval, or the signaling interval. And as you can see, the energy of these signals, energy of S1t is equal to energy of S0t equal to EB. And before we proceed further, we have to say something about delta F, the deviation. Now, delta F is chosen in such a way that it is chosen in such a way that the signals S1t and S0t are orthogonal to each other, or in other words, we can say that their inner product has to be 0. Delta F is chosen in such a way that their inner product is 0, or equivalently the correlation coefficient of these two signals has to be 0. And we can see that if we determine the inner product, we can see that when we replace these signals in the inner product with what we have here, we will end up getting 2 EB by TB, the square roots when you multiply, cos 2 pi FCT into cos 2 pi FC plus delta FT. You can use a simple trigonometric identity and write the result as cos of the sum plus cos of the difference of the arguments, and you get 2 pi 2fc plus delta ft, one of the terms. This will be the cos of the sum of the two arguments of cos plus cos of the difference, which will be 2 pi delta ft, and the whole will be divided by 2. That I can show like this. Anyhow, this is only a proportionality, because what we have to mainly see is what should be delta f set to if this result is 0, because this is the correlation coefficient or the inner product. And we can see that if delta f is an integer times 1 by TB, and remember that fc is already an integer times 1 by TB. If delta f is also an integer times 1 by TB, then this correlation coefficient will be 0. This correlation coefficient, or this integral will be 0. And this becoming 0 when delta f is integer times 1 by TB is quite obvious, because anyhow fc is also already integer times 1 by TB. So 2 into integer times 1 by TB is another integer times 1 by TB, plus integer times 1 by TB is nothing but integer times 1 by TB. So if you integrate that from 0 to TB, the first term is definitely going to be 0. Whereas the second term, you see that EB by TB integral 0 to TB cos 2 pi delta ft dt. When we integrate this, anyhow, first term, this result will be 0. When you integrate this, gives a 0 because delta f is integer times 1 by TB. As I said, fc is already integer times 1 by TB. And this, if you integrate, we can write down the integration here itself. This is what we are integrating. The result will be sine 2 pi delta f t divided by 2 pi delta f. This will be the result of integration, and it is from 0 to TB. The integration happens from 0 to TB. I'm sorry, that's the limits of the integration. So we have integrated this and we get this as results. We substitute the limits now. The upper limit gives us TB minus the lower limit. When you substitute here, you get a 0 because sine 0 is 0. So this gives us this, which is nothing but this. And that, as you know, is proportional to dropping this, because that's just a constant. It is proportional to sinc. It's proportional to sinc to delta f TB. And if delta f is an integer times 1 by TB, TB cancels, 2 into integer is an integer, and sinc of an integer is 0. Sinc 0 is 1, but sinc 1 is 0, sinc 2 is 0, sinc 3 is 0, so sinc of an integer is 0, which means that if delta f is an integer times 1 by TB, this result will be 0, and since this result is already 0 in the integration, when you perform the integration, this will also be 0 because delta f integer times 1 by TB means this becomes 0, which means that the signals S1t and S0t will be orthogonal to each other if delta f is an integer times 1 by TB. And that integer can also be just 1. So delta f we will set as 1 by TB in the subsequent discussion. 2 by TB also works. In fact, any integer times 1 by TB will work, but 1 by TB can give, since delta f becomes, when delta f is 1 by TB, it is definitely less than delta f 2 by TB. So making it 1 by TB, we can minimize the bandwidth. And interestingly, if delta f is 1 by 2 TB, even then the signals will be orthogonal to each other. We will discuss this later when we discuss another modulation scheme. For the time being, we will proceed with the assumption that delta f, as we saw now, has to be an integer times 1 by TB, and it can be 1 by TB itself because 1 is an integer, and that will ensure that these two signals are orthogonal. Now, having fixed delta f as equal to 1 by TB, we note that we can express these signals in terms of the orthonormal basis. Now, before that, I will quickly, for again completion of the discussion, I will sketch a waveform, a rough FSK waveform, binary FSK waveform. Let's say, as earlier, the data sequence is 101, the bit sequence is 101, and let's take, for convenience, this is TB, this will be TB, and this is TB, say. And let's say that FC is 3 by TB, So 3 cycles for 1. So I'm going to use the larger frequency for 0. That need not be the case always. And delta f we have chosen as 1 by TB. So Fc plus delta f will be 4 by TB because this Fc is taken as 3 by TB. So that makes the waveform look like this. This is a freehand sketch. So I can see the frequency is more here, the frequency is less. I'm using a higher frequency for 0. It can be other way also. And then again we have Fc, that is 3 cycles. Yeah. So it may not be prominently visible, but the frequency is more here. 1 by TB times more, 1 by TB more than Fc, which is 3 by TB here. So this is how the waveform looks like, a frequency shift keying waveform looks like. And again, in practice, Fc will not just be 3 by TB, it will be several tens or even hundreds times 1 by TB. And delta F will still be 1 by TB. We can still have 1 by TB and have the two signals orthogonal. And keeping delta F as 1 by TB, as I said, results in a lesser bandwidth for the signal compared to delta F being say 2 by 3B or 3 by TB. Okay, now S1T can be expressed as root EB as we did earlier with binary ASK and binary PSK. We can express this as root EB, root 2 by TB cos 2 pi FCT, again in this same interval. As I said, I may not be able to write that every time, but remember the interval. S naught T is root EB, root of 2 by TB cos 2 pi Fc plus delta F T. And we can now identify this as one of the basis functions and this as the other basis function, and we have already seen that these two are orthogonal to each other, and the energy of this is 1, energy of this is also 1. So these two together form an orthonormal set of two functions. They are individually of unit energy and they are orthogonal, so it's an orthonormal set of two functions, say phi 1t and phi 2t. So I can write S1t as equal to root EB phi 1t. So I'm calling this as phi 1t plus 0 phi 2t, because S1t is just root EB phi 1t. You can add plus 0 phi 2t just to bring the signal, the orthonormal signal, the basis function phi 2t also into play. And S0t would be 0 into phi 1t, just to bring phi 1t into the picture, plus root EB into phi 2t. Effectively, these zeros you don't have to write. What it means is S1t is root EB phi 1t, which is nothing but the same thing. Only thing is that we are identifying this as phi 1t and this as phi 2t. That's the only difference. We are just renaming them, that's all. Okay, now this tells us how we can plot this. In fact, this takes us directly to the signal space diagram and how we can show these two signals, the signal S1t and S0t, which stand for the two distinct binary symbols 1 and 0 or 0 and 1, whichever it is. We see that the signal space is two-dimensional because there are two basis functions involved. So we can draw like this: phi 1t and phi 2t. So you can see that they are orthogonal and of unit energy. They form the basis functions. And S1t, this is root EB, let's say. So this is 0, root EB. So root EB 0. This is the signal point corresponding to the signal S1t. If we want, we can write it as vector S1. And similarly, S0t is phi1t coefficient 0, phi2 is root EB. So this point will be 0 root EB, and that corresponds to the signal point of the signal S0t. So this is how the signal space diagram looks like. It will be a two-dimensional signal space, and the signal points look like this. And this will be root EB, this will be root EB. Now moving on, let us quickly look at the detection schematics. Just as we did with the case of binary ASK and binary PSK, we will use that generalized detection schematic which we developed in the previous videos when we discussed detection theory, and the same thing will specialize to binary FSK as we did earlier. So received signal we have to multiply with S1t minus S0t, in our case root 2 EB by TB cos 2 pi FCT minus, so this is S1t minus this into cos 2 pi FC plus delta FT. So this as a whole is S2t, S1t minus S0t. Then integrate over the signaling interval, sample at the end of the integration interval, that is at TB, to get gamma, feed that to a decision device or decision circuitry, whatever we call it, and then set the threshold, get the decision here, and the threshold will be, in the case of binary FSK, as you know, N0 by 2, natural log P0 by P1 plus E1 minus E0 by 2. In our case, E1 is equal to E0 is equal to EB. Probability of the two hypotheses, that is the two symbols, is 1 by 2 each. So we get EB minus EB by 2, which is 0. So threshold is 0. Threshold will be 0. Now, as we did earlier, since these are proportional to the basis functions, we can also use, to make it look more elegant, we can simply write this as phi 1 minus phi 2t, wherein we scale the S1t minus S0t which we had earlier, we simply scale it, that's all. And the question to you, as I did earlier, is whether the threshold will remain the same if we do this. That is for you to find out. Again, it's an exercise for you. And there is an equivalent way in which you can represent the same thing, which goes like this. The equivalent representation is like this. Received signal is split into two. We multiply here with phi 1t, multiply here with phi 2t. It's the same thing in a different schematic. It's just the same thing. 0 to TB dt. So you integrate separately and sample at t is equal to TB. Sample this also at the end of the integration integral, and you have an adder here, plus sign here, minus sign here. So effectively you will subtract. You can see it's the same thing that's happening, and give it to a decision device and get the decision at the output. Now, if you see here carefully, one can ask what happens, the signal is split into two. So will it not result in a reduction in the amplitude? It does happen so, but that happens to the noise also. So effectively the schematic works exactly the same way as it works here performance wise. So again you have to find out what should be gamma t, because I am multiplying with the basis functions. Find out what should be gamma t here as well. And these schematics which I show here are the coherent receiver schematics. As I said in the beginning itself, we will be first discussing the coherent receiver schematics, also called as correlation receivers, because essentially it's a correlation process that's happening, correlation receiver. And there is an equivalent matched filter receiver in this case also. So that matched filter receiver will look like this. Phi 1 t minus t minus phi 2 t minus t. This will be the impulse response of the matched filter. If you want, you can have S1 t minus S0 t minus t, same thing, except for a scaling factor. Again, gamma t you have to find out what happens instead of using S1 capital T minus S0 capital T minus t. If I use this, what happens to the threshold? If I was using S1 capital T minus S0 capital T minus t, then threshold is 0. Whether the threshold is the same, simple question, you can find out the answer for yourself. And here also you can have a matched filter version. And remember, the two are equivalent. The correlation receiver and the matched filter version are equivalent in this context. Additive white Gaussian noise. Phi 1 t minus t phi naught t minus t. Rather, it should be tb to be more specific, because t was the durational signal we used when we discussed detection. Here we have changed it to tb to emphasize that it is the bit duration. So that small correction you make. So this is the receiver schematics. The previous one is the correlation receiver. This is the matched filter receiver. And finally, we have to arrive at the performance. We have to write the expression for the performance, error performance. What is the probability of error? Again, in the general expression which we derived when we discussed signal detection and estimation, there we substitute the terms, we get q root of, you had E1 plus E0 by 2, that gives EB, because E1 as well as E0 is EB, and then rho is 0 divided by M0. So this is the probability of error for binary FSK, and you can see that it is identical. It is identical to binary ASK. So error probability performance wise, binary ASK and binary PSK are identical. And you can see that EB is the average bit energy. In the case of a binary ASK, if you recall, bit 1 or one of the bits was transmitted with an energy of 2 EB, the other one was transmitted with an energy of 0. So the average is EB. Here both the bits are transmitted with the energy EB, and hence the average is EB. So average energy is kept the same, bit energy is kept the same, and you can see that performance of binary ASK and binary FSK are identical. Binary FSK, and as we saw earlier, binary PSK is better than both of these. There is a 3 dB improvement in the performance of binary PSK compared to binary FSK and binary ASK for same bit energy to noise density ratio. And finally, I'll just give a very simple schematic of the generation of amplitude shift binary ASK, binary FSK, and binary PSK waveforms. Very simple schematics again to complete the discussion. So for binary ASK, the schematics is like this. These are very simple. Only essential parts are shown. 2 by TB cos 2 pi FCT, which is phi t. Remember, there is only one basis function. It's a one-dimensional signal space, binary ASK. The input data, which can be this or this. So root of 2 EB or 0. If it is root of 2 EB, then you get the signal root of 4 EB by TB cos 2 pi FCT. If it is 0, you simply get a 0. So this is the binary ASK waveform. Very simple schematic. Now when it comes to binary PSK, again we have only one basis function, but the difference is here. We take plus or minus root EB, we multiply and we get the binary PSK waveform. So you see, if it is plus root EB, you get root of 2 EB by TB cos 2 pi FCT. If it is minus root EB, you get minus of root 2 EB by TB cos 2 pi FCT. That is the binary PSK. And when it comes to binary FSK, we need a voltage controlled oscillator, and the input D is 1 or 0, one of the two symbols represented as 1 and 0, and depending on these symbols, we can represent these symbols in terms of voltage levels, and depending on those voltage levels, the VCO output frequency will change. Say if it is 1, the voltage level input to the VCO is such that the frequency is FC. If it is 0, say the voltage level is such that the frequency is FC plus delta F. So this is the discussion on binary modulation schemes. We have discussed binary ASK, binary PSK, and binary FSK. We need to now discuss, of course, performance wise we have seen that binary PSK is 3 dB better than binary FSK and binary ASK when it comes to the probability of error. It is possible to show this in a graph wherein we can capture the performance of all three. So the graph will be roughly like this. This is the bit error rate or probability of error. We can call it as bit error rate also, because if the probability of error is 10 power minus 1, it means that 1 out of 10 bits are erroneous. If it is 10 power minus 2, it is 1 out of 100. So we can also call it as bit error rate. And this side we will have this axis will be EB by N0, bit energy to noise density ratio in dB. This is a rough sketch. You can find the scaled figure in the textbooks. And let's say we have something like 10 power minus 25, 10 power minus 20. This is a rough sketch, so the numerical accuracy may not be very good, but still I will try to explain the key features, and probably so this is 2, 4, 6, 8. So this is in dB, 10, 12, 14, 16, say something like this. And the figure would be roughly like this. You will get a variation like this. So let me try to make it as realistic as possible. Say this is for binary ASK and FSK. You know, they are the same, they perform the same way. And the binary PSK1 will be, the binary PSK1 if I show, that would be somewhat like this. It will be somewhat like this. It will be smooth here. Yeah. Now, this difference, if you see, forget about the numbers. Numbers may not be accurate because it's a freehand sketch. If you fix this bit error rate, let's fix this bit error rate, and let's find out what should be EB by N naught for this bit error rate, which I have shown to be between 10 power minus 20 and 10 power minus 15. The numbers may not be correct. These and this may not be correct. It's a freehand sketch, but I will still explain the point here. For a chosen bit error rate, which is this, say between 10 power minus 15 and 10 power minus 20, what should be EB by N naught? And we see that for binary ASK, this is the EB by N naught. Whereas for binary PSK, this is the EB by N naught. And this difference would be 3 dB. So to get the same performance, bit error rate performance or probability of error, binary PSK, this is binary PSK, the blue one is binary PSK. Binary PSK needs 3 dB less EB by N naught than binary ASK and binary FSK. This is exactly what we saw earlier, because we saw earlier that when it comes to binary PSK, we saw that when it comes to binary PSK, the probability of error was q root 2 EB by N naught, whereas for binary ASK and binary FSK, it was q root EB by N naught. So the 3 dB improvement that we see here, the 3 dB difference that we see here is reflected here as well. So that this is the key point. These numbers, as I said, be cautious. They are not correct. It's a freehand sketch. They may or may not be correct. But this is the point that I am trying to drive home here. So the 3 dB improvement in the performance of binary PSK as compared to binary FSK and binary ASK is obvious here. Maybe we'll take one more example. You treat this as an example. We'll take one more example.
A binary digital communication system employs binary amplitude shift keying and transmits data at a bitrate of 50 megabits per second. It is desired to have a bit error rate of less than 10 power minus 4. If the two-sided power spectral density of additive white Gaussian noise is 10 power minus 8 watts per hertz, and the signal power loss from transmitter to receiver is 3 dB, what should be the amplitude of the transmitted signal?
Okay, so the the data given says that the desired bit error rate is 10 power minus 4. 10 power minus 4 is the desired bit error rate, and that implies, of course, bit error rate and probability of error are identical in this case, in the cases that we are discussing now, in the binary modulation schemes that we are discussing now. So a bit error rate of 10 power minus 4, bit error rate of 10 power minus 4 implies or means that on an average 1 out of 10 power 4 bits can only be erroneous. So this is the desired bit error rate. So it means that on an average only 1 out of 10 power 4 bits can be afforded to be received erroneously. That's on an average. It doesn't mean that it has to be exactly 1 out of 10 power 4. It's on an average. And this means, of course, that the probability of error has to be less than or equal to 10 power minus 4, or the bit error rate, the desired bit error rate is 10 power minus 4. If it is better than that, that is, if it is less than that, then it's also well and good. So desired bit error rate is 10 power minus 4, 1 out of 10 power 4 bits on an average. So if it can be less than that, then it's good enough. So we can say that the desired probability of error, or the probability of error, has to be less than or equal to 10 power minus 4. And the modulation scheme that is under consideration, the binary modulation scheme under consideration, is binary amplitude shift keying as given in the problem statement. And we know that for binary amplitude shift keying, the probability of error is given by the expression q of square root of q square root of EB by N naught. So now, since the probability of error has to be less than 10 power minus 4, we can say that q root EB by N naught has to be less than or equal to 10 power minus 4, because P has to be less than or equal to this, P is this, which means that Q of this has to be less than or equal to 10 power minus 4. Now if you take a look at the Q function table, which is widely available, you can see that if you look at the Q function table, you can see that Q 3.7 is equal to, of course, to a certain degree of accuracy, 0.00, you can find this using the Q table, 0.000178. This is the value of Q of 3.7. You can see from the table, and we can see that we can express this as equal to, since it is 10 power minus 1, 10 power minus 2, 10 power minus 3, 10 power minus 4, so we can say that this is approximately 10 power minus 4. So once we see that Q of 3.7 gives you, and we will take this as 10 power minus 4, once you see that Q of 3.7 gives 10 power minus 4, we can say that since the probability of error has to be less than or equal to 10 power minus 4, we can say that root EB by N naught, if this is 3.7, then we get 10 power minus 4. So if it has to be less than or equal to 10 power minus 4, this has to be more than or equal to 3.7. Because larger this argument, smaller will be the value of the Q function. So we want to have root, so as I said, root of EB by N naught, if it is exactly 3.7, we get something very close to 10 power minus 4. So it has to be more than or equal to 3.7 if we want to have a probability of error or a bit error rate less than or equal to 10 power minus 4. Now this means that This means that now here onwards it's a simple manipulation of terms. This means that EB has to be greater than or equal to 3.7 to the power 2 into n naught. 3.7 to the power 2 into n naught. That is 3.7 square into, now if you look at the data again, if you take a look at the data, it is said that the two-sided power spectral density of additive white noise is n naught by 2 equal to 10 power minus 8 watts per hertz. So that means n naught will be 2 into 10 power minus 8. So you can substitute it here, 2 into 10 power minus 8, and if you evaluate this, if you calculate this, you see that you are going to get something like 27.4 into 10 power minus 8, and its energy, so we will put the unit as joules. By the way, in case you calculate this and you get a different answer, you can contact me and we will see who has made the mistake. So the bit energy has to be greater than or equal to 27.4 into 10 power 8 joules, or say 274 nanojoules. That has to be the bit energy. Now we know that in binary ASK, the signals, the received signals, if you recall the previous discussions, the received signals are S1T root 4 EB by TB cos 2 pi FCT, and S0 T is 0 for the interval 0 to TB. You know this. We have been discussing this for quite some time now, the two signals. Of course, in binary ASK, these are the signals. For binary FSK, they are different. For binary PSK, they are different. So now, this means that this calculation now, what we did here, it says that EB has to be at least 274 nanojoules, or more than that, of course. One can say EB has to be greater than or equal to 274 nanojoules, which means that the amplitude of the received signal, has to be 4 into 274 into 10 power minus 9, that is in joules I express it, divided by the value of TB is again implied in the data. It is given in the data in the sense we are told that the bit rate is 50 megabits per second. So if the bit rate is 50 megabits per second, TB will be 1 by 50 megabits per second. That means 10 power minus 6 by 50. So we can substitute for TB here 10 power minus 6, and 50 goes to the numerator. And this gives again, if you calculate this, and you can see if you get a different result anywhere at any point, you can get in touch with me. If you calculate this, you will be getting the result as approximately 7.4. And that means that the received signal has to be, that is to have a bit error rate of 10 power minus 4. The received signals, remember, the received signals amplitude has to be at least 7.4. If it is more than 7.4, your bit error rate will be better, in the sense it will be an improved bit error rate, and probability of error wise it will be a smaller probability, and S0T of course 0. Now it is said in the statement that attenuation of the signal from transmitter to receiver is 3 dB. So the 3 dB attenuation is a power attenuation. So it is clearly said in the data that attenuation of the signal from transmitter to receiver is 3 dB, and the question is what should be the amplitude of the transmitted signal. So this is the received signal. The received signal amplitude has to be this. Now what should be the amplitude of the transmitted signal? So since the attenuation is 3 dB from the transmitter to the receiver, this is a power attenuation. To compensate this, you should have the transmitted signal amplitude as root 2 into 7.4, because you are multiplying the amplitude now, so that the power will be 3 dB more. When you transmit, it will be 3 dB more, so that it can compensate for the 3 dB loss which the signal is going to encounter as it propagates from the transmitter to the receiver. And this is again, to a certain degree of approximation, 10.5. This means that the transmitted signals has to have an amplitude of at least 10.5 for S1T, and of course S0T 0. So this completes the solution. So the answer is that the transmitted signal should have at least an amplitude of 10.5, so that even after suffering the 3 dB attenuation in the course of propagation from transmitter to receiver, the received signal will have an amplitude of at least 7.4. In other words, the received signal will be 7.4 cos 2 pi fct, at least in terms of amplitude. And that being the case, the probability of error when you calculate, you will get Q 3.7 or more. That is, the argument will be 3.7 or more, which means that you will get a probability of error or a bit error rate of 10 power minus 4 at least, or less than that.